Hey everybody, good afternoon. It's Monday the 4th of May. And it's week 7, day 29 of our little bioinformatics-a-thon. Yes, we're good to go this week. And as I think I said at the end of last week, where we want to get to this week, if at all possible, is to derive some differentially expressed genes from our RNA-Seq experiment. The slight spanner in the works of that I forgot about last week is that this week in the UK is a 4-day week. So Friday is a public holiday, so I won't be online on Friday this week. So we've only got 4 days, but I still think we can get a good way towards achieving this. What we're going to do today is what I started to do on Friday, which I probably really shouldn't have done, which was to try and get our count data, which we generated using Salmon at the command line. I want to get that count data into R using the package that I started to introduce on Friday, which is called tximport, and I began working my way through that on Friday afternoon, when perhaps I shouldn't have done. So we're going to kind of recap that now and get that data into R, and then from there we can get that data into the analysis package we're going to use, which is DESeq2. So our first job is to get that count data into R. I do want to mention a couple of things. The first is that I've put a couple of things up on GitHub that might be useful to people. So the first of those is I actually showed you last week. So this is the Lockdown Learning GitHub, which stick the URL there, the URL bar up there. So yeah, github.com/sjcockell/lockdown-learning. In the repository now, there's a few things. The first of which I showed you last week, and that is the SRA run table that I downloaded from the SRA run selector that you can use in conjunction with the scripts from the other weeks to download the data, the FastQ data that we're working with here. So there's that table. That's also the table that we read into R on Friday and then summarized to get us our kind of 12-row table which describes our samples. So if you want to be working from the same table as I'm working from, then you can download that from GitHub. The other couple of things, one is the script where we were generating our plots last week using ggplot2. That is now up as well. And then finally, there is also up there a zip file which is just in the main repository. So in the landing page of the repository, there is a zip file called data.zip, which has all of the data from Salmon that I produced locally inside it. So there are, in that zip file, there are 12 directories containing all of the Salmon data. So all of the outputs from Salmon from my run of Salmon for these 12 samples. So if at any point you have struggled to complete a bit, I know that there's some people who haven't necessarily had enough disk space for all the FastQ files, that some people have had trouble downloading the data from the SRA, which is completely understandable, or any other stage, but you've carried on because you've wanted to continue with the lessons, which I entirely admire, then that data is available there so that you can pick up where we are now with the data that we're all working with, so everybody can have the same data representation in their R session. So if you want to download those files, you absolutely can. I posted on Twitter today a direct link to that data zip. So if you want to download that zip file, track it down on my Twitter and download it from there. So yes, so that's I just wanted to point those things out because I think for some people those things might be very helpful in just making sure that everybody's singing from the same hymn sheet, so to speak. Okay, so with that, we'll go back to R and back to what we were doing on Friday. So I introduced a few different concepts on Friday in quite short order, and I know that some people might have that I may have gone through those things a little bit too quickly. So I talked about 3 different packages from the tidyverse. That's Reader, dplyr, and Magritte. And I also started to talk about tximport. So I'm going to quickly go back over what I did with the tidyverse packages. So I introduced pipes for the first time in R. That's represented by this funny symbol here, this % greater than % combination, which is the equivalent of the pipe symbol in the command line. And in the same way as at the command line, rather than piping the output of one command into another command, you can write the output of one command into a file and then use that file as input for the next command. We can do the same thing with our pipes here at the command line. With the pipes here in R, we can do the same thing but with variables. So instead of this pipe, which I realise for some people can get quite confusing, we can instead save the output of the first command as a variable and then use that variable as input for the second command. So just to show you what that would look like for this particular set of commands here, it would be, so if we do sample table equals read CSV and then the name of the file, like that. So that would create a variable called sample table, which will contain the contents of this comma separated values file. You would then again make sample table equal to the results of the next command, and the next command is going to be select from sample table, and then it's this set of columns. So select takes all of its arguments and uses them as column names and gives you back a tibble where only those columns have been selected, and the first argument for select is the tibble that you want to select from. When we're using it in a pipe, we don't need to pass that first argument because the first argument is the thing that comes in from the pipe. So that's the select. Yes, that's our select there as the second command, and then the third command that we would run would be sample table equals sample table slice. Slice. Sorry, getting carried away. Slice sample table, and then the second argument is then which rows you want to slice. So slice allows you to pull back numerically indexed rows. So what we're passing to slice as the second argument is a vector of doubles, which is the row numbers that we want to get back. And if you remember, we did that with seek. So it was seek. I'll just do it at the console. 148 by equals 4. That gets you every fourth row in your in your tibble, and so reduces us from these four rows per sample down to just 1 row per sample. And I'll show you the effect of these things in a second. So 148 by equals 4. Okay, so first of all, we'll just read in the sample table using read CSV. So that gives us a variable called sample table. If we have a look at our environment, you can see we've got sample table, which has got 48 observations, so 48 rows of 33 variables. So 48 rows, 33 columns. So that's the first thing. Then the second command then selects 6 columns from that data frame, from that tibble, and saves it. Again, saves it using the same variable name, so it overwrites that variable. So we'll run that one, and you'll see that the number of variables will reduce. So it's gone down from 33 variables to 6 variables, and that's because we've just selected 6 columns from the data. And what we then want to do is take a slice of every 4th row in that table to give us, instead of having 48 observations, 12 observations, because we've only got 12 samples. If we have a look at this as it is at the moment, you'll see that every group of, 4 rows in a row are identical to one another. So if you look across these rows, there's nothing different about them. So every single one of the 6 columns has the same data in each of those 4 rows. So we just need one of those 4 rows. Somebody asked a question in the live comments about whether you could use something to do with duplication. The fact that these rows are duplicated, whether you could exploit that in selecting out just a single representative of each set of duplicates. I'm still not really sure how it might be possible to do that. So let's have a quick think, because there is a function which is unique, and unique will let you. So if you've got a vector which has repetitive elements in, there you go. So there's a vector which has got 6 numbers in, 3 of them are the same. Unique will just give you back the unique entries in that vector, like that. So instead of having 3 1s, a 3, a 54, and a 6 in it, this vector now just has 1 1 in it. Whether there's an easy way of removing duplicate rows, I suspect dplyr gives us an easy way. I'm just as I'm mugging to the camera, I'm just effectively looking online to see. I wonder if unique works. Let's have a look. So we've got sample table as it is, has 48 rows. If we run sample table through unique, what do we get back? We get back 12 rows. So it does in fact look like unique will work across the tibble here. So Google was my friend a little bit there, but actually that's a really nice way of doing it. So rather than taking a slice here like this, we could use unique, which is actually a simpler way of doing it, because the rows are exact duplicates of one another. Unique is sufficient to give you back a 12-row sample table. So there you go, that has reduced me to 12 observations of 6 variables. So that's quite a nice way of doing it. It's actually a neater way of doing it than using slice. Quite like that. And that, yeah, so somebody had asked that on Friday, and I hadn't thought about it again until just now. But actually that was worth thinking about. So thanks to whoever it was who asked that. Okay, so that's the sample table that we want. We've got these 12 observations of 6 variables. So 12 rows and 6 columns. And that describes our experiment in sufficient detail that we can use that for analysis should we want to. So then the next job was to use this tximport package to get our count data that was produced by Salmon a couple of weeks ago, and use that to use that count data and get it into R using this tximport package for the import method for getting that data into our R session. tximport, we had a look at the help file on Friday, and I'm not going to go into the same kind of detail as I did on Friday because we pulled out the arguments there that we need by going through all of the arguments. I think that was a bit much, so let's just let's stick with what we've got here, which is we need these tximport needs these 4 arguments. Okay, so files, and we've got to figure out what this argument is. That's our first job, is to figure out the files argument. Type, which we know is Salmon, because Salmon was the software that we used to generate our count data. So the other options there would have been other types of software that's capable of producing this kind of data, but we used Salmon, so the answer for us here is Salmon. This tx to gene, that's the other thing we've got to figure out. We'll look specifically at the help entry for that in a minute. This is going to require us to go back to the command line briefly for a couple of commands to get this sorted. So that's that, and then this ignore tx version, which we've set to true because all of the identifiers in our Salmon output have the Ensembl transcript ID and then a dot and a version, and we don't want the dot and version number after it. So ignore tx version here is ignoring that dot and the number that follows it. So that's just something for the sake of our mappings. Okay. So those 2 arguments are the ones that we need to fill in, and so that's what we're going to do now. So what we're going to do is we're going to look at the help for tximport. So $tximport. So the question mark is like man at the command line. It gives us the help information for that particular function. So here's the help file for tximport, and we want to look at, first of all, we want to look at the files argument. Okay, so this is the first one that we need to define. So files says a character vector of file names for the transcript level abundances. Okay, so this is a vector, a character vector, which contains the names of the files which contain our abundance estimates. So that is the quant.sf files that that Salmon produced. So if we go to the files browser here in RStudio, this is our current working directory. If you remember on Friday, we set up a project which lives in the directory which we created, which is where our data currently is. So each one of these GSM directories is the output of Salmon, and in each one of those directories there is a file called quant.sf, which is the output of Salmon. So these are the files which this files argument needs to refer to. And if you look at them, they contain the file name. They live in a directory which has the sample name. So the name of the directory is the name of the sample, and then it will be /quant.sf. So the path to this GSM 4432378 sample quantification file would be GSM 443278 / and again hitting the tab here in R, and it brings up this little tab complete dialog, and then you can find the thing that you want. So that is the file for that first sample, and what tximport wants here is a character vector that contains one of these for each of our 12 samples. Okay, so the question is, how do we construct that character vector with the information that we've got? The information that we've got is this tibble here, this 12 by 6 tibble, the first column of which, the sample name column, contains the first bit of information that we need, this GSM 4432378. So this is the sample ID, and obviously in our 12 columns we've got, sorry, in our 12 rows we've got 12 different sample IDs. So we can use this information in this tibble together with this this file name, which is the same for each of our samples, to build this vector that we need. So how do we do it? The first thing that we need to do is we need to use a method from dplyr, which is this method called pull, and pull will give you back the contents of a column in a tibble as a vector. So if I subset my subsetted my tibble using select to get just one column out of it, then it would still be a tibble. It would be a tibble with one column, and I couldn't use that as a vector because it's not a vector. It's a tibble with one column. But pull gives me back the column that I ask for as a vector, not as a tibble. Okay, so if we pull from sample table, that's the tibble we're interested in pulling from, and we want to pull one column, and that's this sample name column. We still need the backticks like that. So this command will give me that sample name column from my tibble as a vector. That's not quite what we want. Okay, this isn't yet a character vector of file names of where my quantification estimates live, but it is a character vector. To turn it into a character vector of file names, we have to stick this. I've deleted it now. Hold on. Let's put the example back up here. GSM 78 quant.sf. Right. So to turn it into a file, to turn the entries in this vector into file names like this, we have to stick this /quant.sf on the end of each of them. And we can do this using a function that we've already encountered in my 2 or 3 days of introduction to R. That function that we've already encountered is paste 0, which allows you to, if you remember, sticks together strings, characters into a single character, and if one of the elements, or even both of the elements here, is a vector, then it sticks the second argument to all of the things in the vector in the first argument. Okay, so that will produce me a vector of length 3 where coq has been stuck onto the 3 things in the vector in the first argument. So we can exploit this in exactly this. To use this, we're going to do this in exactly the same way as I've done it here. Okay, so this is a vector. So this is like the this bit here of the command that I've written on the line above. So this pull returns us a vector. So here I've defined a vector explicitly, but this gives us a vector. Paste 0, open brackets, then this is the vector, and then onto each element in that vector, we want to stick the text /quant.sf to turn those from just the names of the samples into elements in a vector which point to where those files live, where those quant.sf files live. So if we run this command, you'll see the results of that, which is that you've got the sample name with then quant.sf stuck after it. They look exactly like this. This is a pointer to the file for this 378 sample, and each one of these is the same thing, but to all 12 of our samples. So this is the vector that tximport wants as its files argument. We need to do one other thing to this for reasons which may not be clear immediately, but which may become clear later. We've not talked about names yet, but we need to name this vector. So I'm just going to save this as sample files equals that. Let's just split this out again across lines, because that's always a nice thing to do. Okay, so that's our sample files vector. We need to give this sample files vector some names. I'll explain why in a second, but and the names we want to give it are the sample names, which again we can pull back out of the sample table like this. And I realise I'm eliding some detail there, so I'll talk about this in a bit more detail. Okay, so let's set it first, and I'll show you what it looks like. So it's common practice in R that vectors are a vector is effectively this list of things, and you refer to the elements of a vector by number. So you have the first element, the second element, the third element, and so on. And that's how this vector, for instance, works. You've got element 1 is this, and element 2 is this, and so on. But it is possible to give those numbers names, to give each of your elements of your vector a name. And that's what we're doing on this line here, is we're setting names for each of the elements of our vector. So that they can't not just referred to by a number, but they can also be referred to by their name. I'll show you what that looks like. There you go. So now, rather than being 1, 2, 3, 4, they are still 1, 2, 3, and 4, but they've also got a name, and the name is here. So this element of the vector, this first element of the vector, is called GSM 4432378. And now we can refer to the elements of this vector not just by number. So sample files 1 refers to the first element of that vector, but we can also refer to it by name. Okay, so GSM 4432378 also refers to the same thing. The reason why this is important in this instance, so this is a useful feature of vectors, and you can use this feature for lots of things, and I have no doubt we'll see this again at some point. It's useful in this instance because with this particular vector, the elements of the vector themselves, that is these file paths, are used to tell tximport where to find the data, and the names of the vector, so that's these bits here, the names are used to give column headers to the resulting data that tximport produces. And if you didn't pass tximport a named vector, those columns would just have numbers. They wouldn't have names, and it would be more difficult to figure out which column represented which sample in your resulting data. So what we're doing by creating this named vector here is we are giving tximport the information it needs to generate a data structure which is going to be most useful to us later on. So this is just a little bit of extra work now, but it saves us a lot of pain later on. For us, with our sequentially named samples and all the rest of it, it wouldn't be that hard to do this sort of post hoc, to do it later, but I'd rather do it up front, and it's good practice to get into the habit of doing it up front. Okay, so this sample files vector that we've created here, that is that's the thing that we need to pass to this files argument of tximport. Okay, so we've created that suitable bit of input there now. The other argument that we need to satisfy is this tx to gene argument. So we're going to go back to the help for tximport, and we're going to look for tx to gene in this list of arguments, and it's here. Okay, so tx to gene, it says a 2-column data frame linking transcript ID, column 1, to gene ID, column 2. Okay. The column name's not relevant, but this column order must be used. So transcript ID in column 1 gene ID in column 2. And what this means is this is a way of tximport matching the transcript IDs, which is the primary identifier that Salmon uses, to their constituent gene IDs. So our transcripts, many of our multiple transcripts make up the expression of a single gene. And what tximport is going to do is it's going to summarize that transcript level expression that Salmon has produced to the gene level. So it's going to take the 4 transcripts from one gene, for example, and summarize them to a single measurement for that gene. So if we have a look, I'm now going to go to my virtual machine. So if you don't have your virtual machine running, now's the time to start it up. I do have mine running from Friday. So if you remember, on Friday, we created this COVID RNA-Seq directory, which is where our R project in our studio is living. And that's where we put all of the data. So we put the SRA run table in there, and we put all of our quant.sf files, so all of our Salmon output in there as well. The one thing we didn't put in here is the GenCode FastA entry, which is actually what I need right now. So I'm just going to have to go and find that. So let me go back up to my share directory. I'm going to use a tool here called Find, which we've not encountered before. So I'll very quickly explain how Find works. So Find is very, very complicated, but very, very powerful. In the simplest way, Find is used to, as the name suggests, find files on your file system. So the first argument for find, it takes a number of positional arguments. The first positional argument is where you want to look. So what directories do you want to look in? So I want to look in my current working directory and everything underneath it. So where I want to look is in dot. Okay. Then the second thing that you need to put is how you want to look, what you want to look for. So I want to look for files by name. So I'm going to use -name. There are other ways that there are other things that you can give find for ways that you want to find files. I can't remember them because I always use name. And I can't remember any of the other ways that you can do it. But there are ways that you can look for files created after a particular time or before a particular time, or files above or below a certain size, and lots of other things besides. But I pretty much always use name. Okay, and I want to find any files which have the word GenCode in them. So I'm using a couple of wildcards in order to match any files that have GenCode in, just to see if we can track down where it lives. And there you go, it's in week 5. So find's really quick and is quite useful, especially if you can't remember the name of your file, or you really can't remember where it was. I couldn't remember which week it was in, which is why I did that just quickly there. So find's useful and can be very helpful. Our transcripts.fasta is in week 5. Okay, so let's have a look at it. Week 5 GenCode.v33. Since we did this, and this is the nature of bioinformatics, since we did this, so we downloaded GenCode in week 5. It's now week 7. GenCode version 34 has been released since we did this. So we are now using a one version old version of GenCode, despite the fact we only did this less than 2 weeks ago. That's because Ensembl 100 was released last week. So Ensembl 100 came coupled with a release of GenCode is always coupled with a release of Ensembl, but not every release of Ensembl bears a release of GenCode. But Ensembl 100 was released last week, and with it GenCode version 34. GenCode version 33 is a reference release though, so it's a stable release that will be around for a while. And GenCode version 33 is coupled to Encode version 99, just for future reference. Okay, so let's have a quick look at this file. And actually what I'm going to do is I'm just going to grep out the sequence ID lines, the lines which begin with greater than. Okay, so I'm going to do grep. Make sure that you surround your greater than with single quotes. Otherwise bad things will happen. Week 5 / gencode.v33 transcripts.fa. Right, so this will give me back the identifier lines, and I'm gonna kill that. I'm gonna pipe that into less, just so we can look at them and they're not all scrolling past the screen. So there we go. So these are our sequence identifiers, and you will see that, for instance, these first two. So ENST 456328 and 450305 both belong to the same gene. Okay, their Ensembl Gene identifier for each of those two is the same. Okay, and then we've got a gene which is comprised of one single Ensembl transcript ID, and then another one, and then this one here consists of two as well. And then if you scroll down this a bit, you will find genes that consist of more than two Ensembl Gene IDs. If you go further down, Ensembl transcript IDs. So this one, for instance, here, this gene. So these 6 lines all have the same gene identifier, but different transcript identifiers. So this gene is represented by at least 6 transcripts. So in order to get a gene level count for this gene, you have to sum up the expression for those 6 transcripts, or more if there are more. What we need for tximport is a data frame which has 2 columns. The first column is the Ensembl transcript ID, and the second column is the corresponding Ensembl Gene ID for that Ensembl transcript ID. Now we can extract that information from this file. It is possible to get both the Ensembl transcript IDs and the matching Ensembl Gene IDs from this file. And I've done this many times before, so because I've processed lots and lots of releases of GenCode over the years for use with exactly this pipeline. So I'm going to show you the way that I've done it routinely, which I know works. Okay, so what I'm going to do is I'm going to create 2 files. One file of the Ensembl transcript IDs and a second file of the Ensembl Gene IDs, and because they're on every sequence identifier line in this file, there is one Ensembl transcript ID and one Ensembl Gene ID. What you end up with is 2 files that are exactly the same length, so the same number of lines, with the IDs in the same order. So then you can stick those 2 files together. So those two files together into one single file, and I'll show you a trick for doing that as well. So we're gonna need to run 3 commands here: one to extract the Ensembl transcript IDs, one to extract the Ensembl Gene IDs, and then a third command to stick those identifiers together into a single file. Okay, so the commands for extracting the information, first of all, are both grep. So we run grep. We want to turn Perl regular expressions on, so that's a $P. We want only the text that matches our expression to be retrieved. So we don't want the whole line, we just want the text that matches our Perl regular expression. And then we want to define our regular expression. So to retrieve the Ensembl transcript IDs, they all begin with ENST, and then they have a set of numbers. And I know from experience, I'm not going to try and count, but there are 11 numbers after the ENST. So we want to match a digit, and we want to match a digit 11 times. So that's an 11 in curly braces. So this will find you every line which has ENST followed by 11 digits. And this will retrieve you only those matching bits. So that's our file name. So if I just run this without capturing the output, you'll see that this gives me back the Ensembl transcript IDs. And there's one Ensembl transcript ID in each of those sequence identifiers in that FASTA file, and only one. And there's also only one gene identifier. And they will come back out in the same order as the transcript identifiers. So that's all of our Ensembl transcript identifiers from that file. We want to capture that in a file, so we're going to redirect the output of that command into a file which I'm just going to call enst.txt. Okay, so that is my Ensembl transcript identifiers. So that'll take a couple of seconds to run because it's quite a big file. And then we want to do the same, but for the Ensembl Gene identifiers. Well, the Ensembl Gene identifiers are identical to the Ensembl transcript identifiers, except they're ENSG identifiers, not ENST identifiers. And so again, if we run the grep without redirecting it, so it's exactly the same grep, but this time for ENSG rather than ENST. And if we run it without redirecting the output, again, you'll see those ENSG identifiers scroll down the screen. And you can see, even when they're scrolling past this quickly, you can see that lots of these are repeated quite a lot of times. And that's because each one of these genes is made up of one or more transcripts, and quite often they are made up of lots of transcripts. So it's never really obvious at the extremes, but if you go into the middle, you will see that there are, so there's one that repeats 3 times, for instance, and there will be ones that repeat dozens and dozens of times in this file. So we want to capture that. We want to save that in a file which we're going to call ensg.txt. Okay, so that's our 2 files that we wanted to create. So one with the Ensembl transcript IDs in it, and a second one with the Ensembl Gene IDs in it. And if we just have a quick look, so we'll look at the head of those files. enst.txt looks like that, and ensg.txt looks like that. So they have the type of identifiers in them that we expect. You will also find that they're the same length. So they both have 227,912 lines. Okay, so, but that's not quite what we want to read into R. What we want to read into R is these 2 things stuck together so that you have one ENST and the corresponding ENSG on the same line, and you can do that with the command paste, which we've not encountered yet. So let's have a quick look at the man page for paste. So paste merges the lines of files. So it writes lines consisting of the sequentially corresponding lines from each file, where file is a unit of input here, separated by tabs to standard output. But you can change the delimiter if you want. So by default it's a tab, but you could change your delimiters by using -D. Okay, so let's just quickly show you how this works. So paste enst ensg. I'm just going to pipe it into head just so we can see what the output looks like. You can see that that gives us our transcript ID and our corresponding gene ID. So it takes the first ENST ID and puts it next to the first ENSG ID, and it then takes the second and puts it next to the second, and so on and so forth, all the way down the file. So this is the input that we want then for R. I'm going to make this comma delimited because we've been working with CSV so far. So I'm going to change my delimiters to be a comma. I'm just going to surround that with single quotes just to be safe. And there you go. So that changes it from being tab delimited to being comma delimited. And now I want to save it to a file. So I want to redirect it. Instead of redirecting it to head, I want to redirect it to a file. And that file is going to be in my COVID RNA-Seq directory. And I'm going to call it gene_map.csv because it's a comma separated value file. Okay, so that is the file that I want to generate, and then I'm going to read that file straight into R. Okay, so that will generate that file, And if we quickly list our COVID RNA-Seq directory, you will see that that file is there, gene_map.csv. We can have a look at the contents of it, gene_map.csv, and see that it is a comma-separated values file with the transcript IDs in the first column and the Ensembl Gene IDs in the second column. It's got no column headers in it, and that we need to remember that when we read it into R. Okay, so it's not got a first line which tells us that these are the Ensembl transcript IDs and these are the Ensembl Gene IDs. So we need to bear that in mind, because the way that read CSV works is it will turn, by default, it will turn the first line of the file into column headers if we don't tell it to do something different. Okay, so for TX to gene, we need a 2-column data frame linking ID column 1 to gene ID column 2. So that's the file that we've just created, but obviously we need to read that in so it becomes a data frame in our our R session. So we do that with, so we're going to call it gene_map, and it's read_CSV, which is the same function from reader that we used last week to get our run table in to R. And in this case, our file is called gene_map.csv. Okay, but we need a couple of extra arguments because, like I said, there's no column headers in that. There's no column headers in that file, and so by default, read CSV will try to set the first row in the file as column headers. So we need to overrule that. And you do it with the col names argument, which is either true or false or a character vector of column names. If true, the first row of the input will be used as the column names. If false, it will generate them automatically, so it will call them x1, x2, etc. Or you can say, you can give it a character vector and it will use the elements of that character vector as the column names. So it's that last option is the thing that we're going to do. So we're going to give it a character vector, which is Ensembl transcript ID and Ensembl Gene ID, just to give our name, our column names, our columns names. Sorry. So we'll read that in. So that's read in that file, and if we just quickly have a look in our environment, we will see that our gene map consists of 227,912 observations of 2 variables. Okay, and if you remember, that number 227912 was, go back to here, it was the number of lines in each of our files. There you go, 227912. So that feels like the right thing has happened. I think there's enough sanity checking going on here that means that we can be pretty sure that that's the correct thing. So that is our gene map, and that is exactly what we need for this tx to gene argument for tx import. Okay, so gene_map is that variable that we've just created. So that's what we plug in there, and that is quite long-winded, but that is all of the input that we need for tx import. So now when we run tx import, it will import our data based on those file names in the first column and map it to genes based on the mappings in this tx to gene column argument. So we're going to capture this as a variable. So this is our count data equals that. Okay, I'm going to run this and we will see what happens. So let's make my console big so we can see what's going on. That makes the console big. Control L to get my prompt to the top. Make that little. Move this around. Just tidy things up a little bit. There we go. So, everybody ready? Here we go. Right, so it's reading in the files. It's using readTSV, which is a reader method. There you go. So we've got 12 files read in. It's processing tx to gene, and then summarising abundance, summarising count, summarising length, and it's done. So it's relatively quick on my machine anyway. Hopefully not, doesn't take too long on everybody else's. Let's have a look at count data then. So we've read that data in. Let's have a look in the environment at count data. Okay, so count data is here, and it says it's a large list. Okay, so it's a list, and it's got 4 elements. So if you remember a list, so we talked about this last week, a list is a data structure in R, which is a little bit like a vector, but whereas a vector can only have scalar variables in, so they have to be single variables, and they all have to be the same type. A list can contain more complicated variables, so a list could be a list of vectors or a list of data frames, for instance, and also all of the elements of the list can be different types if you so desire. So it is possible for your list to contain sort of disparate data types, basically. So what's in this list? And if we click on this little blue arrow here, it will show you the entries in this list. So we have one called abundance. Okay, so the abundance entry is numerical, so that's what the num means, and it's got these dimensions. So 60,000, about 60,000 rows and 12 columns. Well, we've got 12 samples. 60,000 is the number of genes. So that's an abundance element in our list. We've got a counts element, which has the same dimensions. We have a length element, which again has the same dimensions. And we have counts from abundance, which is set to no. It's just a character which is set to no. So the most important entry in here is the counts entry. Now, because this is a list, we can extract that entry if we want to. So there's lots of ways of doing it, but we can do count data 2 square brackets. I don't know if people remember this. We went over it relatively quickly. And then the name of the element that we want to extract. There you go. So that's our counts. It doesn't print very well because it's quite large. But if we find the dimensions of it, there you go. You'll see it has 60,000 rows, just over 60,000 rows. That's our genes, so a row per gene, and 12 columns, so a column per sample. Okay. So what we're seeing here is the top 100 rows or so, I think, of that data frame. It's a data frame, so we're seeing some of that data represented here. So for this gene, Ensembl Gene ID 3, you have 280. Your count in the first sample is 218, 253, 600, 365, and then in the next sample, just go scroll down a bit, it's 205, 158. 555. So this is our count data. This is the number of reads in each of these samples that mapped to transcripts that belonged to these genes. So this is our count data. This is the input for the next step in our process. You could also get this not just with the double square brackets, but you could get to it with the dollar notation. So count data $, and then you get an autocomplete. So these are all of our options for this. The other things that have come in here, by the way, are the other numbers that you find in the quant.sf file. So if we have a quick look at, so if we head COVID GSM 78 quant.sf. So you've got length, effective length, TPM, num reads. The other elements of our data frame, you've got the length that comes out of that file as well, and you've got the abundance, that's the TPMs that come out of that file as well. And then the counts is the num reads entry. So you've got num reads is the counts here, TPM, that's the abundance, and length is used for the length of the gene. The length is important for normalization purposes, which we'll talk about tomorrow when we put this data into DSeq. Okay, so count data dollars counts gives me back the same information as I had there, and because that's a data frame, I can subset that as well, so I can get the first 6 rows of it. Just to show you a slightly smaller slice of that data. There you go. So that's the first 6 rows, the first 6 gene IDs with all of their counts. So that is our data. That's our count data imported from the results of Salmon into R. Now, obviously, there's been a little bit of a hiatus from finishing work with Salmon to getting that data into R, because we had to introduce R in between those two things. But hopefully we've now got to a point where we have got to a point now where we have that data, that all important count data, read into R, summarized at the gene level, and ready to analyze. So tomorrow we're going to get this data into DSeq, and we'll have a look at normalization, how normalization works tomorrow. And we'll take a look at the PCA plot that DSeq produces tomorrow as well, because that's relatively straightforward to do. So we'll get this data into DSeq tomorrow. We'll start to think about the way that DSeq works and the maths that DSeq applies to this count data. Okay, so I think we've done well today. It's something I probably shouldn't have started going through that on Friday, but we could take a step back today and get it done properly. So I'm pleased that we've done that. So yes, that's all for today. Hopefully that's been useful, and hopefully everybody's with me and has got the data in R now, and we're ready to go with the next stage. So thanks for tuning in. Thanks for dropping by. If you've turned up today because you read my tweet and you thought you'd drop by, then welcome. Come back tomorrow if you've enjoyed it. Come back tomorrow if you haven't enjoyed it, if you're a masochist. For those of you that have been here for 6 weeks, thanks very much, and I hope to see you again tomorrow as well. We see the same names cropping up in the live comments every day, which is really nice to see those loyal listeners. So maybe we can attract some more loyal listeners and keep that going. So thanks everyone. See you tomorrow. Have a good evening. Signing off. Bye. Stay safe. Keep well. Bye.